At 828 meters above the streets of Dubai, the Burj Khalifa rises higher than any other completed building on Earth. But height alone is not what makes this tower extraordinary. So, how does a building more than 800 meters tall remain stable? It is nearly 3 times the height of the Eiffel Tower. It contains 163 occupied floors, thousands of tons of steel, and enough concrete to build a substantial town. Powerful desert winds, extreme temperatures, and the gradual movement of concrete over many years. If the Burj Khalifa had been designed like an ordinary skyscraper, it could experience serious twisting, excessive movement, and structural failure. The answer begins below the ground. Dubai is famous for sand, and sand does not sound like the ideal place to support the tallest building in the world. However, the Burj Khalifa does not simply sit on loose surface sand. Engineers investigated the ground beneath the site and found layers of sand, sandstone, and other relatively weak rock. Instead of depending on one solid layer of bedrock, the foundation was designed to spread the immense weight of the tower through a large volume of ground. Directly beneath the building is a reinforced concrete mat, measuring 3.7 meters thick. It contains approximately 12,500 cubic meters of concrete and was constructed in 4 major pours. This mat acts like an enormous structural platform. It spreads the load from the walls and columns over a much wider area, but the concrete mat alone is not enough. Underneath it is a group of board-reinforced concrete piles. Each pile is approximately 1.5 meters in diameter and 43 meters long. These piles do not work only by resting on their ends. Much of their capacity comes from friction developed along their surfaces. Imagine pushing a long wooden stick deep into compacted soil. Pulling it out becomes difficult because the surrounding ground grips the entire surface. The piles beneath the Burj Khalifa work according to a similar principle, but on a far greater scale. The building load travels down through the concrete walls, into the foundation mat, through the piles, and finally into the surrounding ground. The concrete used for the foundation was designed with low permeability. This was important because groundwater in Dubai contains chlorides and sulfates that can damage concrete and corrode its steel reinforcement. The foundation, therefore, had to resist both physical pressure and long-term chemical attack. But a strong foundation solves only the first problem. The next challenge is the shape of the tower itself. From the air, the Burj Khalifa does not look like a normal square or rectangular building. Its floor plan is shaped like the letter Y, with 3 wings extending from a central core. This shape was partly developed to provide good views and natural light for the hotel rooms and apartments. More importantly, it became the foundation of the tower's structural system. The system is known as a buttressed core. At the center of the building is a strong 6-sided concrete core. Extending from this core are 3 structural wings. Each wing contains reinforced concrete walls and columns. The clever part is that every wing supports the other 2 wings. If wind pushes against one side of the tower, the forces are transferred through the central core and shared with the other wings. The structure behaves like a giant 3-legged support. The central core provides resistance against twisting, while the wings resist bending and sideways movement. A single concrete core standing alone would need to be extremely large and heavy to achieve the same stability. By connecting the 3 wings to the core, the engineers made much more of the building participate in resisting the wind. This means that walls serving ordinary spaces, such as corridors, hotel rooms, apartments, and service areas, also perform important structural work. The system is strong, but also efficient. Its strength is distributed through a connected network of concrete walls, columns, and floor slabs. At selected mechanical levels, structural outriggers connect the central structure to the perimeter columns. These outriggers make the outside columns participate in resisting the tower's movement. It is similar to widening your stance when somebody tries to push you. The wider support makes it more difficult for your body to tip. Gravity is always present, but for a tower of this height, wind becomes one of the most important design forces. Wind flowing around a tall building creates areas of positive and negative pressure. It can push the building sideways, twist it, and cause it to sway. A certain amount of movement is normal. Every tall building moves slightly. The aim is not to make the tower completely motionless. The aim is to control the movement so that the structure remains safe and people inside remain comfortable. One of the most dangerous wind effects is called vortex shedding. As wind passes around a building, rotating pockets of air can form alternately on each side. These vortices create a repeating sideways force. If that repeating force begins to match the natural movement of the building, the motion can increase. This is known as resonance. It is similar to pushing a person on a swing. Small pushes, applied at exactly the correct rhythm, can gradually create a much larger movement. The designers of the Burj Khalifa used an unusual method to prevent the wind from establishing this rhythm. They changed the shape of the building repeatedly as it rises. The three wings do not continue straight to the top. Each wing steps back at different heights. The floor plates become smaller, and the position of the setback spirals around the tower. Because the tower has a different shape at different heights, the wind cannot organize itself into one powerful and consistent pattern. Engineers sometimes describe this as confusing the wind. More than 40 wind tunnel tests were carried out during the development of the tower. Engineers tested rigid models to measure structural forces. Flexible models were used to study the tower's movement. Local pressure tests examined the forces acting on the glass facade. Other tests considered wind conditions around entrances, terraces, and surrounding streets. The results allowed the designers to adjust the building's orientation, dimensions, and setbacks. Remarkably, the predicted movement remained within accepted comfort limits, without requiring an additional tuned mass damping system. Some tall buildings contain a huge moving weight near the top. As the building moves in one direction, the weight moves in the opposite direction and helps reduce the motion. The Burj Khalifa does not rely on such a system. Its stiffness and aerodynamic shape manage the wind through the structure itself. The material used for most of this structure is reinforced concrete. Concrete is very strong under compression, which makes it suitable for supporting the enormous vertical loads. Steel reinforcement inside the concrete provides additional strength and helps control cracking. The Burj Khalifa used approximately 330,000 cubic meters of concrete and 39,000 tons of reinforcement steel. However, using concrete at this height created another challenge. Concrete had to be pumped hundreds of meters above ground level. As pumping height increases, the pressure required becomes enormous. The concrete mixture must remain fluid enough to travel through the pipe, but stable enough that its materials do not separate. Concrete was pumped from ground level to a record height of approximately 601 meters for the reinforced concrete structure. Special high-strength concrete mixtures were developed. The concrete had to perform in Dubai's heat while still providing the required strength, workability, and long-term durability. Much of the concrete work was completed at night, when temperatures were lower. This helped control the temperature and quality of the mixture. But concrete does not remain exactly the same size forever. Under continuous load, it slowly deforms through a process known as creep. It also contracts slightly as moisture leaves the material, a process known as shrinkage. In the Burj Khalifa, small changes repeated across hundreds of meters could produce significant differences. The concrete walls and columns could shorten by different amounts. If this movement were not predicted, floors could become uneven, partitions could crack, pipes could be damaged, and the facade panels could move out of alignment. The engineers carefully adjusted the dimensions and reinforcement of the walls and columns. They tried to keep the stresses in different vertical elements at similar levels. The construction team also allowed for future movement. Some parts were deliberately built slightly away from their final theoretical positions. As the structure settled, crept, and shrank, these elements gradually moved closer to their intended positions. Temperature created another major engineering problem. Dubai experiences intense sunlight and very high summer temperatures. One side of the tower can heat and expand, while another side remains cooler. The glass and metal facade must accommodate this movement without breaking or allowing water and air to enter. The exterior contains close to 26,000 glass panels. Each panel was individually prepared, and the glass includes a special coating to reduce solar heat gain. The aluminium and glass facade reached a height of 512 meters, setting a record at the time for facade installation. The tower also experiences a strong stack effect. Warm air tends to rise inside tall enclosed spaces. In a building more than 800 meters high, the difference in temperature and air pressure between the bottom and top can become substantial. Without careful control, doors may become difficult to open. Unwanted air may rush through lift shafts, and smoke could move rapidly during a fire. The building is divided into separate zones. Mechanical floors contain pumps, electrical equipment, water tanks, and air handling systems. Water cannot be efficiently pumped from the ground directly to every tap near the top. The pressure at the lower levels would become far too high. Instead, water is pumped in stages and stored in tanks at different heights. The same principle applies to vertical transportation. The Burj Khalifa contains 57 lifts and 8 escalators. Rather than every lift traveling from the ground to the highest level, the tower uses different lift zones and sky lobbies. This reduces travel time and prevents lift shafts from occupying too much valuable floor space. Fire safety also had to be reconsidered for a vertical city. People cannot simply walk quickly from the highest occupied floors to street level. The stairways are enclosed in fire-resistant, reinforced concrete, and pressurized, air-conditioned refuge areas are provided at intervals through the tower. These protected areas give occupants a safer location to wait during an emergency. Above the main concrete structure is the tower's telescopic steel spire. The spire contains more than 4,000 tons of structural steel and rises for more than 200 meters. Major sections of the spire were assembled within the building and raised into position using hydraulic equipment. The upper structure gradually changes from reinforced concrete to lighter structural steel. The Burj Khalifa opened on January 4th, 2010, after years of design, testing, and construction. Its success did not come from one miracle material or one oversized foundation. It came from making every part of the building work together. The foundation distributes the load into the ground. The concrete core resists twisting. The three wings support each other. The outriggers engage the perimeter columns. The setbacks disrupt the wind. The concrete mixture provides strength and durability. The facade manages heat and movement. The surface floors divide an 828-meter tower into manageable sections. That is the real engineering lesson of the Burj Khalifa. Extraordinary height is not achieved by making one element unbelievably strong. It is achieved by controlling how thousands of individual elements share forces, accommodate movement, and respond together. It does not defeat gravity. It guides gravity safely into the earth. It does not completely stop the wind. It changes the wind before the wind can control it. And that is how the tallest building in the world stands, without falling over. This is engineering behind buildings. Great structure has a story. Subscribe and support us to discover the next one.